Hello, my name is Jonas Mikkel, and this is Lab 2, Motion of a Falling Object. So for my introduction, I'm watching the motion of a falling object, and in my case I used a flat cloth mask, and then I compared two GLOWSCRIPT models using information from the experiment to predict the final position of the object. So in Model 1, there's only the force of gravity used, no air resistance or drag, and in Model 2, we're using drag and gravity in the equation, which drastically changes the final position and velocity. And in the final product, we evaluate the data to see the effect of drag on the object. So for some basic physics principles, I got the equation for net force, final velocity, and final position. So in net force, the equation is mass times change in velocity divided by change in time. For final velocity, it's initial velocity plus net force times change in time divided by mass. And for final position, it's initial position plus the product of current velocity and change in time. Alright, and then to find net force, you have to add up all factors of force, which is, in this case, it can either be only gravitational force or gravitational force plus drag force. So to solve gravitational force, you do mass times negative g, which is gravity constant, 9.8 newtons per divided by kilogram, times j hat, which is direction of the constant. So it's going straight down, which is why it's only in the y-axis. And for drag, it is negative b, proportionality, constant of drag force, found by trial and error. The magnitude of velocity, which is speed, times v hat, the direction of velocity. So in my experiment, the mass of the object was 0.0012 kilograms, which is 12 grams. The initial position is listed there, and the change in time is 0.333 seconds. So here's to watch the video. Here I drop the object, and then the tracker follows it. As you can see in the y-axis, it goes straight down. So in my GLOWSCRIPT, this is the first GLOWSCRIPT code without using drag, which is why B is 0. So first I input all necessary values, mass, initial position, change in time. Then I update the formula for FNet, which is also listed in the about 2 slides ago. Then I correct the velocity update formula and correct the position formula, and that's it for this code. Now moving on to the drag code, this one's a little bit different. You input the same values, and then you find B by comparing the final position of the code and the tracker and make sure they match up. And then input the drag force equation, which then updates the formula for FNet, where you add gravitational force plus drag force, and then correct the velocity update and position update formula. So here's the graph of all the positions. So for the tracker, it's the dots, that's what we're going by. The drag and gravitational force line, it starts off the same as only gravitational force, but then because of the air resistance, it comes up a little bit, which matches in line with the position of the tracker info. But the only gravitational force will continue to accelerate, and it only goes straight down, which is not in line with the tracker. So comparing GLOWSCRIPT velocities, so in the drag force graph on the right, you can see that the graph it comes up a little bit, kind of evens out, while the no drag force continues to just go straight down without any resistance or stopping, showing that when trying to find terminal velocity, it is only possible to find it when drag is included. On the other hand, what if the object was thrown downwards? So by changing the code on the top right, I changed the vector to 0, -1, 0 to show that's the initial velocity getting thrown down. And by looking at the graph, the velocity and time graph, the object still continues to level out around 0.3 seconds. So it shows that terminal velocity still will be achieved even if the object is thrown down with the force.